Hello everyone, very good morning to one and all. Welcome you all in the next lecture of heat transfer. Whether my voice is audible and can you see my presentation? Let me know, please comment in the chat box. Okay, great. So we'll wait for 2 minutes so that remaining student can join and then we'll start. Okay, so in the last lecture, we have started our main core chapter, that is nothing but conduction, and we have discussed the difference between thermodynamics and heat transfer. So we come to know that the thermodynamics deals with the equilibrium state of substance, whereas the heat transfer is non-equilibrium state. In thermodynamics, we come to know that how much amount of energy or work has been done, or the amount of energy has been performed or used to convert that particular state, or from one equilibrium state to another equilibrium. The substance changes its phase. At that time how much work is consumed or how much energy is consumed, that we come to know from thermodynamics. Whereas the thermodynamics does not tells us about the rate of conversion or the time required to perform that particular process or to complete that particular process. Whereas the heat transfer tells us the temperature distribution of temperature distribution inside the body, as well as the heat, the rate of heat transfer or time required to complete that particular process. So that we will come to know from the heat transfer phenomena. Okay. Then we have discussed about the conduction. So conduction is heat transfer, one of the heat transfer phenomena. So heat transfer is nothing but what? The transmission of energy from one region to another region because of a temperature gradient or a temperature difference. That is nothing but a heat transfer. So whereas the conduction is nothing but transfer of heat from one part of a substance to another part of a substance. Okay, that is nothing but within a substance, or from one substance to another substance, which are in physical contact, physical contact, and that will happen without appreciable displacement of a molecules, and that will happen without appreciable displacement of a molecule. Also we have discussed the examples of heat transfer within a substance. Okay, that is nothing but from one part of a substance to another part of a substance. Okay, we have heated this particular rod at this particular end, but the heat will transfer from this hot region to the cold region of that particular rod. So that is nothing but heat transfer within a substance. Whereas To understand the heat transfer between two substances, we have considered this particular orange orange substance and blue substance, and when they are in a physical contact, the orange substance is having higher temperature than this particular blue substance, and the heat will transfer from this particular orange substance to the blue substance, and after some time the equilibrium state will be achieved. That is nothing but the temperature of two substances will be same, and there will not be a further change in the temperature. Okay, and the heat transfer will be stopped. Okay, so that is nothing but the conduction. Okay, that is nothing but the conduction. Now we have also discussed that there are two phenomena for the transmission of heat by conduction in a solid. So first one is the lattice vibration, and second one is the transport of a free. Okay, so lattice vibration means what? Once the heat is received in one of the region of the region of a substance, then that particular molecules get heated. Okay, that region molecules will get heated, and they start vibrating at their main position. Okay, while vibrating they collide on adjacent molecules. They collide on adjacent molecules, and during that collision they transfer the heat to the another molecules, or adjacent molecules, or adjacent molecules. Okay, so similar kind of process will be carried forwarded, and it will be transfer the heat from one region of a substance to another region of a substance. Okay, so lattice vibration is the one of the phenomenon to transfer the heat by conduction from one region of a substance to another region of a substance, or from one substance to another substance. Whereas the another phenomenon is nothing but a free electron. Now free electrons are available only in the metals. Okay, so this phenomenon will be seen in in metals only, in metals only. Okay, so the free electrons from the higher temperature region and the lower temperature region, we can say that the electric flux will be formed, and the electron will transfer from high temperature region to the low temperature region. Okay, electrons transform from high temperature region to the low temperature region, and in this manner heat will be transformed from high temperature region to the low temperature region. And because of that, in metals the two phenomena will happen. Okay, in metals two phenomena will happen. That is nothing but lattice vibration also, uh, and we can say that electron transformation also, so that metals are good conductors of heat, whereas in non-metal the free electrons are not available. So only lattice, the heat will be transferred because of a lattice vibration only. Okay, because of a lattice vibration only, or we can say that the molecular vibration only. Okay, so that the non-metals are uh, having less capability to transfer the heat, having less capability to transfer the heat as compared to the metals, Okay, so then further we have also discussed that how this particular conduction phenomenon of a heat transfer is happening in gases and liquid. Okay, so we know that the gas molecules are randomly moving here and there. Okay, and when they collide with each other and they transfer their momentum and energy with the another molecule, so that is nothing but what the kinetic energy of a molecule will be transformed. Okay, so we know the kinetic energy. Okay, and in a similar manner, when the two molecules collision will happen, okay, at that time the molecules are in a physical contact. Okay, so at that time the higher temperature molecule, wait 1 minute. लिंक ब्रेक होते हो मध्येच. So when the collision of two molecules will happen, at that time uh, the higher temperature molecule will transfer the heat to the lower temperature molecule. So in this manner the conduction will happen in a gases, and in a similar manner in a liquid also, whereas the liquid molecules are very close to each other as compared to the gaseous molecule. So when they when the liquid molecules comes into contact, higher temperature liquid molecules comes into contact with the lower temperature liquid molecules, at that time the heat will be transferred from the higher temperature molecule to the lower temperature molecule. So in this manner, this conduction phenomenon also happen in a gases and liquid. So conduction phenomenon will be present in gases, liquids and solids also. Okay, gases, liquids and solids also. Okay, getting everyone? Now, the further thing, the important part of this chapter or this particular bit is nothing but Fourier's law of heat conduction. Okay, the Fourier's law of heat conduction. The whole chapter will be depend on this particular law only. Okay, so try to understand the basic law of heat conduction, that is Fourier's law. Okay, so for that purpose, I will repeat this once again because it having the more importance. If you understood these things, then you'll understood the further things as early as possible. Okay, so first of all, we have considered one slab or one block. Okay, and that particular block is having the surface area. Okay, one side surface area, we can say that this side surface area is capital A. Okay, this side surface area is capital A, or we can say that the two surface areas having areas of A. Okay, both the sides having areas A. Okay, so and this surface is maintained at a T1 temperature. Okay, this surface is maintained at a T1 temperature. Now the another surface, okay, other side of this particular block having another surface which is maintained at a T2 temperature, which is maintained at a T2 temperature. Okay, so now this T1 temperature or this surface temperature T1 is greater than the T2 temperature. Okay, T1 is greater than the T2 temperature. Okay, so the heat will be transformed from this particular surface to backside surface. Okay, this particular surface to the backside surface. As we know the basic rule of heat transfer, that is nothing but heat is always transforming from high temperature region to the low temperature region. So the heat will transform from this surface to the backside surface. So we come to know that the heat transformation direction, heat transfer direction. So this red line shows that heat transfer direction. Okay, whereas the Q is the heat transfer rate. Okay, and that we have to determine. Q is the heat transfer rate and that we have to determine. Okay, so basic things we know that the surface area is capital A. Okay, this surface is maintained at a T1 temperature and backside surface is maintained at a T2 temperature, whereas the thickness of this particular slab is dx. Okay, and what tells the Fourier's law? What tells the Fourier's law? So Fourier's law tells us that the rate of flow of heat through a simple homogeneous solid is directly proportional to the area of the section at right angle to the direction of a heat flow and change of temperature with respect to length of the path of the heat flow. Okay, change in temperature with respect to length of the path of the heat flow. Okay, first thing is nothing but what? The rate of heat transfer or rate of heat flow is directly proportional to what? The surface area. Which surface area? Perpendicular to direction of heat flow. Surface area, which surface area? Perpendicular to direction of heat flow, and also directly proportional to what? Change in temperature. Change in temperature means what? T2 minus T1. Okay, another side surface temperature minus this particular previous surface temperature. That is nothing but change in temperature, T2 minus T1 with respect to what? Change in length. Okay, or the length of path of heat flow. So how much distance need to travel by heat to reach to another surface? So that is nothing but what? The thickness of that particular slab. Okay, the thickness of that particular slab. So that much distance need to travel by the heat to reach to another surface, to reach another surface. So distance traveled by the heat is nothing but the thickness of that particular slab, and that is equal to dx. That is equal to dx. Then according to our Fourier's law, we can write the equation that rate of heat transfer means Q. Okay, Q is directly proportional to surface area perpendicular to heat transfer. Surface area perpendicular to heat transfer. Okay, or normal to heat transfer. That is nothing but capital A multiplied by change in temperature with respect to with respect to change in length, or the length which is traveled by heat. The length which is traveled by heat, that is nothing but dt divided by dx. Dx is our thickness, and that much length is traveled by heat. That much distance is traveled by heat. Okay. So q is directly proportional to a multiplied by dt divided by dx. q is directly proportional to a multiplied by dt divided by dx. Okay, getting everyone how we have converted this statement into a equation format, how we have converted this particular statement in a equation format. Now further is nothing but we have to remove out this particular proportionality sign, and we have to normalize this particular equation. Okay, so for that purpose we need to introduce one constant. For that purpose we need to introduce one constant, and so that we have introduced k as a constant, and here proportionality sign will be removed out and equal to sign will be inserted over here. So we can say that q is equal to minus k multiplied by a multiplied by dt divided by dx. Okay, so now here we have introduced minus sign also. Okay, we have discussed only that to remove the proportionality sign we have to introduce the constant. Okay, k is the constant, but why we have introduced the minus sign over here? Now uh, we should have a focus on this temperature only. dt means what? Dt means temperature between the two surfaces. Dt means temperature difference between the two surfaces. Two surfaces is, first surface temperature is T1 and next surface temperature is T2. So difference we are always taking the next surface minus initial surface. Okay, next surface minus initial surface. So that will be dt will becomes T2 minus T1. dt will become T2 minus T1. But heat is always transforming from high temperature region to the low temperature region, so that T1 is greater than T2. Okay, so that T1 is greater than T2. So T1 minus T2 will provide you a negative value. Will provide you a negative value. T1 minus T2 will provide you a negative value. To accommodate that negative value, okay, we have provided here a negative sign. To accommodate that negative value, we have provided here a negative sign, so that our equation becomes q is equal to minus k multiplied by a multiplied by dt divided by dx. Okay, further we have rearranged this equation in the format of a heat flux, and heat flux is nothing but q divided by a. Okay, heat transfer rate per unit area, that is nothing but a heat flux. Okay, so q divided by a is equal to minus k multiplied by temperature gradient, that is nothing but dt divided by dx, or we called it as a change in temperature with respect to change in length. Change in temperature with respect to change in length. Okay, so q divided by a is nothing but heat flux, that is nothing but heat transfer rate per unit area. Heat transfer rate per unit area. Now any doubt, anything? Shall we move ahead to the next point? Now you clear the Fourier's law? Is there any doubt, any question? Please comment in the chat box, understood or not understood.
Sir, can you explain heat flux definition once more?
What?
Heat flux definition once more, sir.
Heat flux. Heat flux means what? The heat transfer rate per unit area. Okay? Heat transfer rate per unit area. That is nothing but a heat flux. This quantity will be called as a heat flux. Okay? Samajhte? Okay? Just we have transferred this A to this side. Okay? And we have rearranged this equation. We have just rearranged this equation as Q by A. So Q by A is called as a heat flux. Okay, and its unit will be watt per meter square. Its unit will be watt per meter square. Getting heat transfer rate per unit area is nothing but heat flux. Now it is clear or not? Okay. Okay. So we have just further we have discussed that their significance or the quantity we have taken over here, what is the meaning of that particular quantity? So Q is nothing but what? Rate of heat transfer. Okay, Q is nothing but what? Rate of heat transfer, and its unit is watt. Okay, always take the unit of Q is watt. Okay, then second is capital A. Capital A is nothing but heat transfer area or available heat transfer area, and its unit is meter square, and that area should be normal to the direction of heat flow. That area should be normal to the direction of heat flow. Okay, then here we come that small q. Okay, here I have not provided any symbol for the heat flux, but for the heat flux we have to consider the small q as a symbol. Okay, small q as a symbol. So small q is nothing but heat flux, and this heat flux unit is watt per meter square, and this heat flux is nothing but, or the unit of heat flux is watt per meter square. Okay, then dt divided by dx is nothing but temperature gradient. Dt divided by dx is nothing but temperature gradient, and its unit will be degree celsius per meter. Its unit will be degree celsius per meter. Now the last point, we have introduced one proportionality symbol, and that symbol is nothing but k. Okay, k is called as a constant of proportionality, and it is also called as a thermal conductivity. In this particular law, k is called as a thermal conductivity. K is called as a thermal conductivity. Getting everyone? Any question, any doubt? Okay, so now to apply this particular law, we need to consider some assumption. To apply this particular law, we need to consider some assumption. Okay, so following are the assumption on which Fourier's law is based. Okay, first one is conduction of heat takes place under steady state conduction. Okay, conduction of heat takes place under steady state conduction. So steady state means what? There will not be change in temperature with respect to time. Okay, there will not be a change in temperature at a particular position with respect to time. So that is nothing but a steady state heat conduction. Okay, that is nothing but a steady state heat conduction. Now the heat flow is unidirectional. Okay, so there are multiple directions. We can say that the proper direction of a heat flow, we can't assume that in which direction heat is flowing, but for the assumption purpose to implement the law, we have to assume that heat is flowing in a one direction only. Heat is flowing in a one direction only. Okay, heat is flowing in a one direction only. To implement the law, this particular assumption is most important, because uh, uh, actually there are 3D view. We have discussed that here the 3D view. Okay, so in 3D view we can say that if the temperature is here T1 degrees Celsius, this heat flow, heat will be transferred in this direction also, this heat will be transferred in this direction also, this heat will be transferred in this direction also. Okay, in any direction heat can flow, but for the implementation of a law, we need to consider that the heat is flowing in a one direction only. Heat is flowing in a one direction only. That is nothing but unidirectional heat flow. Then the temperature gradient is constant, and the temperature profile is linear. Okay, temperature profile is linear. Okay, then there is no internal heat generation. Okay, there is no internal heat generation means what? Heat generation means what? If you consider the example of heater. Okay, heater is example of heat generation. Okay, so continuously it generate heat, but for the heat transfer, to implement this particular law, initially we have to consider that there is no heat generation in that particular body. That is nothing but what? There is no internal heat generation in that body. We have not provided any current to that particular body, so that that body will generate the heat. Okay, so there is a simply maintained temperature of a two surfaces, or maintained temperature of that particular body, and there is no heat generation in that particular body. Okay, so that is the assumption to implement this law. And the last one is the nothing but the material is homogeneous and isotropic. The material is homogeneous and isotropic. Okay, the homogeneous means what? Homogeneous means what? There is a similar composition in every direction. And isotropic means what? Oh, homogeneous means what? The homogeneous material is nothing but we can say that the material composition is similar in all direction. Okay. Now the next thing is nothing but we have to understand what is meant by thermal conductivity. We have to focus on thermal conductivity. Now just here only we have discussed this particular equation. We have considered this equation only. So this equation we will consider as equation number 1. Q is equal to minus K multiplied by A multiplied by dt divided by dx. Okay. And from this equation we try to understand what is meant by thermal conductivity. Okay. We try to understand what is meant by thermal conductivity. Okay. So give heading as a thermal conductivity of a material. Consider equation number 1. Okay. Equation number 1 as Q is equal to minus K multiplied by A multiplied by dt divided by dx. Okay. Now we have to rearrange this particular equation. We have to rearrange this particular equation as K is equal to Q divided by A multiplied by dx by dt. Okay. K is equal to Q divided by A multiplied by dx divided by dt. Now just here what we have done, first of all we have absorbed this negative sign inside the temperature. Okay. We have absorbed this negative sign now. Okay. Over here. And we have transferred this K on this side. Okay. And Q on this side. Okay. We have transferred all this, or we can say that all the parameters we have transferred on one side, and we have converted this equation in the form of a K. Okay. So the equation will be K is equal to Q divided by A multiplied by dx divided by dt. Okay. Dx divided by dt. Okay. So dx we have transfer on that side. It will be Q A we have transfer on that side, and dt we have transfer on that side. So remaining part is K only. Okay. And this negative sign we have absorbed inside the bracket. Okay. Or this dt will absorb this negative sign. In that case dt will becomes T1 minus T2. In that case, if you absorb this negative sign inside the dt, then this dt is nothing but T1 minus T2. Okay. Dt will becomes T1 minus T2. So in this manner we have converted this equation number 1, initial our law equation, we have converted this equation in the form of a K. Okay. That is nothing but K is nothing but our thermal conductivity. K is nothing but thermal conductivity. So K will be interpreted as K is equal to Q divided by A multiplied by dx divided by dt. K is equal to Q divided by A multiplied by dx divided by dt. Okay. Now we have to find out the unit of this particular K. What will be the unit of this particular K? We need to derive that particular unit. Okay. So for that purpose, we have to consider the units of all the parameter on this side. Okay. So first one is nothing but heat transfer rate Q. So Q unit is watt. Okay. Q unit is watt. Then A is nothing but perpendicular surface area for the heat flow. So A unit is meter square. A unit is meter square. Okay. Multiply by dx is nothing but change in length. Okay. Or length. The unit of length will be considered as a meter. So dt is nothing but temperature change. Okay. Change in temperature. So that we can consider in a degree Celsius also, and we can consider in a degree Kelvin also. Okay. So degree Celsius or degree Kelvin. Okay. So that will be unit for this particular change in temperature. Okay. So this meter and here square will be cancelled. This meter and square will be cancelled. Okay. So we will get the unit of thermal conductivity as watt per meter degree Celsius or watt per meter degree Kelvin. Okay. We'll get the unit as watt per meter degree Celsius or watt per meter degree Kelvin. Okay. So any of the unit can be satisfy the importance, or we can say that any of the unit you can use for this particular K. Okay. There will not be change. If you use the degree Celsius also, no problem. If you use the Kelvin also, no problem. Because to convert the degree Celsius, we have to add the 273 in a degree Celsius temperature, and then it will be converted into a degree Kelvin. Okay. But we have to add this in a 2 temperatures. Okay. We have to add this in a 2 temperature. So If you add 273 and if you minus that particular 273, you will get the same value only. You will get the same value only. So for that purpose, we can say that the unit or the value will be same for watt per meter degree Celsius unit, and also the value will be same for watt per meter Kelvin unit. Okay, समजते सगळ्यांना? Getting everyone? How we have derived this particular thermal conductivity unit. Okay. Is there any doubt, any question? Please note down this thermal conductivity of a material. Thermal conductivity of a material. What we have considered initially, we have considered this equation only. Okay, this equation only. Q is equal to minus K multiplied by A multiplied by dt divided by dx. Okay, we have considered that equation only. And just we have rearranged this equation in this format. Okay, just we have rearranged this equation in this format in the form of a K. Okay, that is nothing but thermal conductivity. So after rearranging, K is equal to Q divided by A multiplied by dx divided by dt. Okay, rearrange means what? We have transferred the terms on another side. Okay, K we have transfer on this side, it will become Q divided by A. Dx divided dt divided by dx we have transfer on this side, it will become dx divided by dt. Okay, that much only we have done over here. And negative sign we have absorbed for the temperature. So temperature T2 minus T1 will become, once the negative sign will be absorbed inside the bracket, so it will become T1 minus T2. Okay, it will become T1 minus T2, and that will be our equation for the thermal conductivity. So thermal conductivity is equal to Q divided by A multiplied by dx divided by dt. Next, we have to derive the unit for this particular thermal conductivity, and uh, for that purpose, we have to consider this all the units of this particular parameters. So unit of Q, that is nothing but heat transfer rate, is watt. Unit of Q is watt. Unit of area, capital A, is meter square multiplied by dx is change in length. The unit of length is meter, and the unit of change in temperature. Okay, change in temperature we can use degree Celsius or degree Kelvin. Okay, we can use degree Celsius or degree Kelvin. Okay, so our unit will be watt per meter degree Celsius or watt per meter degree Kelvin. Okay, any of uh, two units you can use uh, for the significance purpose or while solving the problems. Okay, so because we have discussed that to convert the degree Celsius into Kelvin, we have to add 273 degrees Celsius, 273, so that the degree Celsius will be converted into a degree Kelvin. Okay, and we have to add in both the temperature. Okay, so we are taking the temperature difference. Okay, T1 minus T2. So we have to add 273 in a T1 temperature. Also, we have to add 273 in a T2 temperature. So adding the uh, 273 and subtracting 273 will provide you the same value. Okay, so the value will be same for the both the units. Okay, value for the same uh, uh, for both the units of a K. Okay, so K will unit of K is nothing but watt per meter degree Celsius or watt per meter degree Kelvin. Getting everyone? Is there any question, any doubt? Please note down this particular point: thermal conductivity of a material. Okay, shall we move ahead to the next point? Now, we have to define this particular thermal conductivity. What will be the definition of thermal conductivity? Now, here we have to consider that, or we have to define the thermal conductivity in such a manner that when thermal conductivity will be 1, okay, for any material, when thermal conductivity will be 1, okay. So when thermal conductivity for any material will be 1, when Q is equal to 1, that is heat transfer rate will be equal to 1 watt, then area equal to unit area, okay, and temperature gradient dt divided by dx will be equal to 1, okay. For a particular material, if these things will be happen, in that case the thermal conductivity will be equal to 1, okay. ज्यावेळेस Q1 असेल, एरिया 1 असेल आणि हा dt डिवायडेड बाय dx हा जो प्रपोर्शन आहे ते 1 असेल, त्यावेळेस thermal conductivity तुमची काय असणार आहे, 1 असणार आहे. बाय दिस पर्टिक्युलर इक्वेशन the k is equal to 1 if the heat transfer rate will be 1 watt, and that heat transfer through 1 unit or unit area with temperature gradient of 1, okay, temperature gradient of 1 degree Celsius per meter, okay. So in such a manner we can define the k, okay. So definition of k, that is nothing but thermal conductivity is nothing but the amount of heat generated, heat energy conducted through a body of a unit area, okay, and unit thickness in unit time when the difference in temperature between phases causing heat flow is unit temperature difference, okay, is unit temperature difference. काय विचार काय इंटरप्रिट करते ही डेफिनेशन, when k equal to 1 or k is equal to q, okay, when k is equal to q, when k is equal to q, when a is equal to 1 and dt divided by dx is equal to 1, at that time the k value will be equal to the q value, okay, k value will be equal to the q value, okay. So according to this, the amount of heat generated, heat energy conducted, amount of heat energy conducted through a body of a unit area and unit thickness in unit time when the difference in temperature between phases causing heat flow is unit temperature difference, okay, is unit temperature difference. Getting everyone? Definition of this particular thermal conductivity. Now, from the equation number 1, previously we have considered, we can say that material with high thermal conductivity are good conductors of a heat, whereas material with a low thermal conductivity are good insulator. Okay, how we have justified this particular statement? So equation 1, or we have to consider this particular equation. Okay, this is our equation number 1. So Q is equal to minus K multiplied by A multiplied by dt divided by dx. Okay, now if Q value increases, okay, or the Q value is higher one, so in that case the Q value will be higher one, okay. ज्यावेळेस तुमची थर्मल कंडक्टिव्हिटीची व्हॅल्यू जास्त असेल त्यावेळेस Q पण जास्त असणार आहे, ओके. ज्यावेळेस थर्मल कंडक्टिव्हिटीची व्हॅल्यू कमी असेल त्यावेळेस तुमची Q ची व्हॅल्यू पण काय असणार आहे, कमी असणार आहे, ओके. So when the K value will be higher, in that case the heat transfer rate will be higher. When the K value is lower, in that case the heat transfer rate also get lower, okay, will get the heat transfer rate lower one, okay. So that here is justified. So material which transfer the heat within a less time, that material is called as a good conductor of a heat, and the material which transfer very less amount of heat, then that material is called as a good insulator, then that material is called as a good insulator. So we can say that the material with a high thermal conductivity are good conductors of a heat, whereas the material with a low thermal conductivity are good insulator or bad conductor of a heat. Good insulator means it prevent the heat transfer, okay, that is nothing but it is a bad conductor of a heat, that is nothing but good insulator, that is nothing but good insulator. समजतंय सगळ्यांना? Getting everyone? the meaning of this particular line or that particular sentence. Okay, so please note down the definition of thermal conductivity. Thermal conductivity. So you first write this particular equation, then you will come to know how we have defined this thermal conductivity. Okay, so K is equal to Q divided by A multiplied by dx divided by dt. Okay, K is equal to Q divided by A multiplied by dx divided by dt. The value of K is equal to 1. The value of K is equal to 1 when Q is equal to 1, A is equal to 1, dt divided by dx is equal to 1. K is equal to 1 when Q is equal to 1, Q is equal to 1, A is equal to 1, dt divided by dx is equal to 1. So how one can define this thermal conductivity? The amount of heat energy, the amount of heat energy conducted, the amount of heat energy conducted through a body of unit area, through a body of unit area and unit thickness in unit time when the difference in temperature between phases causing heat flow is unit temperature difference. From equation 1, we can say that material with high thermal conductivity are good conductors of heat, whereas material with low thermal conductivity are good insulator. So insulator means what? Which will oppose the heat transfer. That materials are called as the insulators. Okay, so wood is the insulator. Okay, we can say that rubber is the insulator. Okay, so cotton rope is the insulator which oppose the heat transfer. Okay, which will oppose the heat transfer. That is nothing but what? The rate of heat transfer through the material is very less. Why this rate is very less? Because that particular material thermal conductivity is very less. Okay, that particular material thermal conductivity is very less. Because of that, the rate heat transfer rate through that particular material is very less. Okay, so we can say that the materials and good conductor means what? Our metals are the good conductors, because the thermal conductivity of metals are higher as compared to the insulator, and this particular metals will transfer the heat with a higher rate. Okay, or the rate of heat transfer in metals is very high, and the thermal conductivity of the metal is also high. Okay, the thermal conductivity of the metals is also high. Okay, getting everyone? Now we will stop here, or here we can conclude that conduction of heat occurs most radially in pure metals. Now here segregation is there. Okay, how it will impact on a materials, on the basis of a material, because the thermal conductivity is the property of a material. Okay, thermal conductivity is the property of a material, and it will change with respect to material. Okay, So for rubber it will be different, for metal it will be different, for rope it will be different, okay, for cement it will be different, for brick it will be different. So uh, it differs with composition, it differs with the material, okay. So there are n number of thermal conductivities you will get in a single material as we are going to change the composition of that particular material, okay, as we are going to change the composition of a particular material. So the the pure metals having higher thermal conductivity as compared to the alloying material. Alloying means what we are doing in the alloying? Alloying means what? We are adding the impurities in a base material, okay. We are adding the impurities in a base material, that is nothing but alloying. So if you consider that in cast iron, if you add uh, the ferrous, nickel, chromium, then the composition of that particular cast iron will goes on changing, okay. So in a similar manner the thermal conductivity of that particular materials also goes on changing, okay. But the remaining, or we have to remember one thing, that the base metal or the pure metal material or the metals having higher thermal conductivity than the alloying metals, okay, or alloying materials, okay. And the thermal conductivity is very less in a non-metals, okay, in a non-metals. So it is a property of a material depends essentially upon the following factor, okay. So this is the property of a material and it will depend on a following factor. Which are that factor? First one is a material or structure, okay. Second thing is moisture content of that particular material. Then third thing is density of that particular material, and last one is the pressure and temperature, okay. So this material structure, then moisture content and density of material is the part of a substance, but this pressure and temperature are the operating conditions or operating factors, okay. Pressure and temperature are the operating factors. We can operate, we can change this particular factor, but we can't change for this particular factors of a material, okay. Material structure, then moisture content and density of a material, okay. Getting everyone? Getting everyone? So if you have any doubt you can ask, or else you can put up your roll numbers in the chat box. Have you cleared the doubt related to the thermal conductivity? Is there any question, any doubt? Okay, then we will stop here. Just put up your roll numbers in the chat box and you can leave this particular meeting.